Welcome back, everyone. We're going to apply all that we've learned so far about electromagnetic induction in this particular example. We're going to try and predict what direction the needle on the voltmeter is going as we place and we move a magnet into a coil. Now remember, you could be moving the coil inside a fixed magnet. That's fine. They've just got to move relative to each other. But for the moment, let's just use this example. So to remind ourselves a little bit, let's first of all go back to a normal circuit. And we looked at this earlier. We recognized conventional current is from the positive end of a battery to the negative end. So the direction of the current would be around in this direction. And what we're seeing here is this is the positive terminal of the voltmeter, and this is the negative terminal of the voltmeter. You can see where the current is coming in is closest to the positive terminal, and where the current is leaving, it's closest to the negative terminal. The direction of the current across this resistor is from the red to the black. And that's why this is a positive reading here. And that's how we must make sure that we can predict in which way the voltmeter is going to read. Is the current going in at the terminal that is marked positive, or is it going in at the terminal that is marked negative? If it goes in at the terminal marked positive on the voltmeter, it will give a positive reading. If it goes in at the terminal marked negative, it will give a negative reading. So it's very important that we put all the little pieces together so we can make our prediction. And so here we go. Here is our scenario, and we're going to first of all think about it and work through it and see if we can make a prediction. Then we'll go and look at the simulation and see if our simulation is correct. So in this example, let's say that the magnet is moving into the coil in that direction. We've already established when that happens that this end must be a north pole as well. And then using the right-hand solenoid rule, we recognize the current must be going down on this side and all the way down, and if you follow this line, it will go up on that side, it will go in that direction, which means the current is going in at the negative, and it's going to be coming out at the positive all the way around to here, and in the background, it will go up there and it will come down, and there we've got the whole scenario. So if you use our right-hand solenoid rule, we can predict the north pole will be on that side, and we recognize that it's going in at the negative and out of the positive of the voltmeter. So what do you think that means? In which direction is that needle going to go? Is it going to head towards the positive end, or is it going to end towards the negative end? You need to make it clear in your mind, but let's go and test it. You see, this is what I love about science. We can make a prediction, and then we're going to go see if we're right, if our thinking is correct, and let's hope that we are. And here we go. We've got the north pole over here, and we're going to move the north pole towards this coil. Now, I haven't put the field lines on because they're sometimes a little confusing, but I'm going to move it in, and what did you see? As it moved in which direction did that needle go? There, it's going towards the negative. And what did we say? We said that as we move it in, it will go towards the negative. Now, notice what else happens. As we move it in, it moved towards the negative. As we pulled it out, it went towards the positive. And that is exactly what we predicted as well. Remember, if the one end is a north pole when you move it in, if you try and take it out, it wants to pull the north pole back, and so it will swap poles. It will go to the south pole. And if it goes to the south pole, then we'll be able to see which way the current is going. The current will go in the opposite direction. In other words, it will go in at the positive and out at the negative. But let's make sure that we've got that, and we're going to have another look at it. So let's go back to our original diagram. It's go back to our original diagram and let's have a look at what we're going to do here. So in this scenario, what we're going to say is let's predict what will happen, and we're just going to confirm our prediction if we move the North Pole in that direction. So remember what will happen. Think about it carefully. Remember, the magnetic flux is changing. Because the magnetic flux is changing, we're going to get an induced current. We're going to get an induced current because it's a closed circuit. There's going to be an EMF induced across the terminal, and that's what's causing the charges to move, the charges to flow. When we move that North Pole out, remember the crazy teenager who can't make up their mind? What's going to happen? The North Pole is running away. They say, come back, come back, come back. So how are they going to make the North Pole come back? This end has to be a South Pole, because the South Pole is going to attract the North Pole. The North Pole, they will repel each other. The South Pole here will attract. And if the South Pole is attracting, what do we do with our right-hand rule? Well, we take our right hand and we say, we don't want this end to be a North Pole anymore. We want this end to be the North Pole, because that end has to be the South Pole. And if that's the case, right-hand rule, notice now, the current has to be going in the opposite direction to which it was earlier. So that means that it's coming in at that side. And that means that it must be going up over here, and it must be going along over here. And I've marked all these points, so it goes in at the positive, and it's going to come out at the negative through the light bulb, and so we've got the completed circuit. And in which direction is the needle going to go? Well, if it goes in at the positive, then we're going to predict it's going to go positive deflection in that way. And that's just what we've seen. So we've put the things together. Remember, the order that we recognize is, first of all, there's got to be a change in magnetic flux. If that magnet is just sitting there, it's going to do nothing. It's going to stay a reading on the voltmeter of 0. But if there's a change in magnetic flux, the magnet is moving in or out, or the coil is moving in or out relative to the magnet, there's going to be a change. There's going to be an EMF induced. And so what we recognize, if there's a change in magnetic flux, then we're going to say there's an EMF induced. And now we're going to say in which direction. We're going to apply Lenz's law. We're going to use the right-hand solenoid rule. Right-hand solenoid. And if you've got the right-hand solenoid rule, you can then decide in terms of the direction of the current. And the direction of the current will then help you determine the direction of the needle. So there are multi-steps there, but I hope that you can see by looking at these step by step, one by one, you'll be able to master this whole idea. Now, we can do this over and over again, but we're not going to do that. What I'd rather do is say, so what does this mean if we've got a different representation? What does this mean if the picture looks a little bit different to what we've had before? So here's what I'm going to do, is I'm going to say this piece of wire and this piece of wire are connected to the voltmeter over here, where this side is the positive end and this side is the negative end. Now, that's how we've set up the circuit. Now, I want us to be very clear about what we're going to do. And let's make sure that we've got this right. Let's say, in this case, we're going to move the North Pole away. Think about it. If we're moving the North Pole away, what's going to happen to the end of the coil? Well, according to Lenz's law, this end has to become a south end because it's going to oppose the motion that is being made. It tries to undo and put back where it was. So it calls the magnet back to where it was. So it's going to make that end the south pole. Now, if that's a south pole, then I need to recognize using my right-hand solenoid rule that this end must be a north pole. For that to be true, I've got to recognize that for the bottom coils here, the current is going to, see my thumb is pointing to that side, the north pole. The current is going to come out of this side. Current is coming out of this side. Current is coming out of this side. And it's going in on this side. So the current is going in on this side. And if the current goes in on this side, then we recognize that it's going to go down here and it's going to go in at the negative. And if it goes in at the negative and out at the positive, in which direction is the needle going to go? Well, we said if it goes in at the positive and out at the negative, then it will go in the positive direction. So in this case, the needle will be deflected to the negative, will go negative. Okay. So guys, there are multiple combinations of this type of question that they can ask you in a test or an exam. Please just practice. Use the simple, clear thinking that we've established and make sure that you've learned the laws. Before we go, I just want to pick up on two little points. The first one is, so what's the use of all this? Remember I said to you that this was probably the most important discovery of the 1800s. The whole set of work that was done in the 17 and 1800s actually opened up the field of physics for us and helps us to understand a whole lot, even as much as what the light is and the televisions that you're watching this on and the devices you're looking, all started because of an understanding of electromagnetic induction. And so even on this picture where we have power lines, the reason I've shown this is because power lines are indicating to us the way that electricity is taken from the power station, usually far away from the city, and then brought closer to our homes. And for that to work and for us not to lose lots of energy, you need a transformer. Now, for a transformer to work, even your cell phone little charger has a transformer in it. And for that to work, you need to have the principle of electromagnetic induction. Without electromagnetic induction, transformers wouldn't work, generators wouldn't work, and we would be much the poorer. So let's make sure that we are grateful to a great man, Michael Faraday, for discovering this principle. Not just discovering it, making it clear to us, making it useful so that we can today have benefits of the work that he did. Now, final thing, summary for you. Remember, changing magnetic flux is required to induce an EMF across the ends of a coil. The induced current is directly proportional to the rate of change of magnetic flux, and we use the principle of electromagnetic induction for transformers and generators. Thank you for joining me today. I hope you've enjoyed our initial introduction to electromagnetic induction. Please join me again as we continue the story in our next lesson.